are a part of each and every reaction, especially in organic chemistry. So, let's say if A reacts to give you B, now A does not directly react to give you B in most of the reactions. A first reacts, or rather A and B react to give you C, and this C is the transition state and it is temporary in nature. And C again reacts. C then, of course, breaks up to give you D. So, this stage C, this is the transitory stage, and this is the reaction intermediate. So, A plus B reacts to give you C, and then C, of course, gives you D, that is the product. Now, there are various reaction intermediates in organic chemistry. Number one is carbocation. I'll give you the examples of some of them. Then you have carbanion. You have free radicals. And then you have carbenes. So these are some of the reaction intermediates which we'll be studying. So let's first understand one more topic before we proceed into this, and that is fission. Fission actually implies breaking or cleavage of a molecule. Let's take this reaction. Hydrogen breaks up to give you H plus H. But how does it break? No, H2 actually is made up of two hydrogen atoms. That is, you have two electrons of hydrogen shared between two atoms of hydrogen. Now, if we see the electronegativity of this hydrogen is the same as the electronegativity of this hydrogen. So, they do not differ in electronegativity. So, when they break, this hydrogen walks off with one electron and this hydrogen walks off with the other electron. So, you have H dot plus H dot. Now, this H dot is nothing but a free radical. It comprises of an unpaired electron, which are very, very fast, reactive intermediates in chemistry. Because this unpaired electron will try to pair up as fast as possible. So they are very, very, very reactive. Now this we have seen the case of hydrogen free radical. Let's take it with respect to carbon atom. If I have a molecule of methane in which both the carbon have two electrons shared in between them. Now again, there is no difference of electronegativity between these two carbon atoms because they both are atoms of the same element. In fact, they both are the same species. So when they break up, this will walk off with one electron. Let's say this. And the other electron will be taken away by this here. So we will have CH3 dot plus CH3 dot. So now you have two methyl free radicals. I am writing FR over here. Now let's look at the order of stability of these radicals. You have methyl free radical here. Now, this hydrogen is neither electron releasing nor does it attract electrons. Let's take primary free radical. In the primary free radical, one of the hydrogen is replaced by an alkyl group. Now, this alkyl group is an electron releasing group. Now, this solitary electron over here, this is actually a kind of botheration for this carbon atom. And this, on top of that, this alkyl group is electron releasing. So, it will divert more electrons towards carbon, because of which the carbon will be destabilized. As a result, methyl free radical is more stable than this primary free radical. This is the methyl free radical. Okay, I can write it like this. In words, methyl free radical. Then, of course, we have the secondary free radical. In the secondary free radical, one more hydrogen is replaced by an alkyl group. Now, these two alkyl groups may be same, they may be different. And so we now have two alkyl groups which are releasing electrons, diverting electrons towards carbon, which makes the carbon even more unstable. So the secondary carbene ion is even more unstable than the primary or the methyl one. And in the last case, we have the tertiary carbene ion, in which all the hydrogen atoms are replaced by alkyl groups. Just a sec. So you have this here. So this is even less, this is rather the least stable. So if we see the order of stability, methyl free radical, that is CH3 dot, is the most stable, followed by primary, followed by secondary, and the tertiary free radical is the least stable. There is no difference of electronegativity, as we have seen in both the cases. This kind of fission is called homolytic fission. And this gives rise to free radicals. There is yet another type of fission, and that is heterolytic fission. Hetero means different. Hetero means different, and lytic means to break up. So when there is difference of electronegativity, whenever there is difference of electronegativity, heterolytic fission will occur. And this heterolytic fission gives rise to two types of species. One is the carbocation, and another is the carbene ion. That is carbon with positive charge here and carbon with negative charge here. Let's discuss about carbocation in one go. So we'll take carbocation. Here. Supposing I have methyl chloride here, there is a bond between carbon and chlorine, in which chlorine, is very electronegative. So when this breaks up, chlorine, due to its electronegative tendency, it will walk away with both the electrons. So you will have carbon left with a positive charge and chlorine walking away with both the electrons. This carbon is called carbocation or carbonium ion. This is again very unstable because it tries to get rid of this positive charge. Anything in the universe is unstable if it carries a positive charge carries a negative charge, or carries an unpaired electron. So let's look at the stability of carbocation. You have the methyl carbocation here with a positive charge. Now hydrogen group is not electron releasing, so this methyl carbocation is not stable. It will try to get rid of this positive charge by combining with a negative species. So now you have, if I substitute one of the hydrogen atoms by an alkyl group like this, then this alkyl group is electron releasing, as I said previously. So it will try to reduce some of the positive charge of carbon. So इसको थोड़ी शांति मिलेगी. This will get some peace of mind. So as a result, this primary carbocation will be stable than the methyl carbocation. In the next case, if I substitute this hydrogen atom also by an alkyl group, then I have, now both the alkyl groups may be same, may be different. This is a secondary carbocation. Now in the secondary carbocation, I have two alkyl groups which release electrons towards carbon carrying a positive charge, and this gets some respite. Then in the last case, we have all the hydrogen atoms being replaced by alkyl groups, and these alkyl groups, as I said, are electron releasing, so they will try to lessen the charge on carbon. As a result, this carbocation, that is a tertiary carbocation, will be the most stable. So the order of stability will be tertiary is more stable than secondary, is more stable than primary, is more stable than methyl. Okay. Next, of course, we have the carbanions. Now supposing here we have a molecule that is CH3X, in which X is more electronegative than carbon. That is, electronegativity of X is more than that of carbon. So in this case, what happens? Here. The electronegativity of carbon is more than that of X. So carbon is more electronegative than X. So in this case, what happens? Carbon will walk away with both the electrons. So you will have carbon carrying a negative charge and this walking off with a positive charge. So let's look at the stability, and this is the carbanion. Let's look at the stability of carbanion. So you have, this is the methyl carbanion carrying a negative charge. Now you know hydrogen is not an electron releasing group, nor is it an electron withdrawing group. So this will not be, you can say there's no effect of carbon as such, hydrogen as such on the negative ion. Let's take another example. You have one of the hydrogens replaced by an alkyl group, and here you have hydrogen, and this carries a negative charge. Now you know alkyl group is electron releasing group, so it will intensify the negative charge on carbon over here. So this primary carbanion will be less stable than methyl carbanion. Then let's replace this hydrogen also by an alkyl group. So you will have this two alkyl groups here. They may be same, they may be different. Now you have two alkyl groups releasing negative charge towards the or negatively charged carbon that is carbanion. So what happens is the negative charge on carbanion, it intensifies, so it will again be unstable. Then of course in the third case you have all the hydrogen replaced by all the hydrogen are replaced by alkyl groups, and these again intensify all the more the negative charge on carbon atom. As a result, this is the least stable. So the order of stability of the carbanion is methyl is the most stable, then you have primary, then you have secondary, and then you have tertiary. Okay. Then you have the hybridization of free radical. The free radical is sp3 hybridized. The carbocation is sp2 hybridized, and the carbanion is again sp3 hybridized. So you can even see it. You have carbon here, hydrogen here, hydrogen here, hydrogen here, and the electron here in case of free radical. So this is sp3 hybridized. That is the free radical. Then you have carbocation. This, as I said, is sp2 hybridized. So you have H, you have H, you have H positively charged. So this is trigonal. It is sp2 hybridized. Then of course you have the carbanion. This is carbon, H, 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 and you have the two electrons here. So this is sp3 hybridized. I hope you like the video. Please like, share and subscribe.